So we've convinced ourselves that linear search really is linear. It says using indirection, if I got a list of elements, even if they're arbitrarily complex, because of indirection I can get to any element in constant time, and therefore the search is linear because at worst I've got to look at every element once. Still kind of annoying if the list is long. So can I do better than length of the list or linear search for search? Well, the answer is if I don't know anything about the values of the elements, no. If they're arbitrary elements and I have no structure to the list, I'm going to have to look at every element at least once, in the worst case, in order to determine if something's there. So I'm stuck with this. But in some cases I can do better. And in particular, what if the list were ordered? Suppose that the elements were sorted in ascending order, where a simple way to think about it is they're numbers, but they could be more complex things. I've got some way of deciding how to order them in sequence. In that case, I could improve things. And here's a simple search algorithm. It says, given a list L and an element E, I'm going to walk through the list, so for I going from 0 all the way up to the end of the list, and I'll check to see is the ith element equal to E. If it is, I can stop and return true. If it isn't, I'll keep going, but I can be clever. In particular, if the ith element is greater than E, remember I said they're sorted in ascending order, so if I get to a point in the list where that thing is bigger than the thing I'm looking for, I know it can't be in the rest of the list, because they're all bigger than that point. So I can stop right there and return false. If I get all the way through the list and I haven't found it, again I'll return false because it wasn't there. Nice little trick. What does it do to the complexity? Well, it improves the average complexity, but it doesn't improve the worst case. Because in the worst case, I still will go all the way through the loop until I get to this clause down here and I return false. But, even though I haven't improved the complexity with here, I can use that idea in a slightly better way. Notice what I did here was I used the idea that I knew the ordering of the list to be able to cut off some computation right there. Once I got to a point where the element was bigger than the thing I'm looking for, I knew it wasn't in the last half of the list. Let's use the same idea, but more effectively. And in fact, we've already seen this idea when we did bisection search. So we can use this idea of binary search much more effectively. In particular, we would say the following. Let's pick a point, an index into the list that divides the list in half. And let's ask right there, is that the thing I'm looking for? If I am, great, I'm done. But if not, then I can ask the same question I just did before, which is that element of the list either larger or smaller than E? But depending on that answer, I can reduce the search. So what this says is if I've got a big long list here, I'm going to look at the middle element. If it's the one I'm looking for, great, I'm done. But let's assume that in fact that middle element is bigger than the thing I'm looking for. Then I can throw away this entire list and focus on now just searching in this remaining list. And I can do the same thing. Let's look at the middle one of those and say, is that the thing I'm looking for? If it is, great, I'm done. If not, for example, in this case, let's assume that that element is smaller than the thing I'm looking for. Then I can throw away all of this portion of the list and refocus here. We've seen this trick before. We're going to narrow down the range of things we're looking for, cutting in half at each stage what we have to look at. And we're taking advantage of the ordering of the list here. So this now is a new version of a divide and conquer algorithm. I'm going to break up into smaller versions of the problem, a smaller list, plus some simple operations. And the nice thing I know is that the answer to the smaller version is the answer to the original problem. That is, if I find the list or the element in a smaller list, that means I found it and it was in the bigger list. If I don't find it in the smaller list, it means it wasn't in the bigger list and I'm done as well. Okay, let's build some code to do this. Here's a very nice little algorithm for searching a list using binary search. I've got an internal piece of code here that I'm going to use, and let's look at what that does. It says, basically, given a list, an element, and a low and a high point in that list, a low index and a high index, what am I going to do? If high is equal to low, it says I got a list of length 1, so I just return the Boolean value of whether that element's the thing I'm looking for or not. That's all I got to do. If, however, I don't have just one element in the list, I got more than that, I'm going to find a midpoint. And in particular, I'm going to calculate the midpoint by taking the value of the low end of the list, or the low end of the range in the list, and the difference between high and low divided by 2. So I'm taking the range that's left, cutting it in half, and adding it to the index of the starting point. That gives me a new midpoint right there. And then, what do? I check that point. If it's what I'm looking for, I'm done. Otherwise, I check to see, is the value of the list bigger than the thing I'm looking for? And if it is, I'm going to call recursively search again with the same low point, but a reduced high point. And that was what I just diagrammed earlier. It says, if in fact the thing I'm looking for is less than the thing I just checked, I can throw away the entire right half of that list. On the other hand, if it's less than, then I throw away the lower half of the list, and I compute a new low point. And I just keep calling recursively until I either run out of things or I find the thing I'm looking for. To start this up, I'm going to check to make sure that in fact I have a non-empty list. If the list is empty, nothing's there, the element can't be in it, I return false. Otherwise, I'll call binary search. Notice one little subtlety here. I'm reducing midpoint by 1 there and increasing midpoint by 1 there to make sure that I don't look at the same element every time. It's a minor nuance, but it's going to improve things. Here's my binary search. It's cutting down the list in half at each stage by either taking the upper half or the lower half based on this test right here. Okay, I want to answer 2 questions. The first one is, does this actually work? Does the recursion halt? We've talked about this before when we talked about recursive functions, and I want to just remind you, a nice way to deal with this is to create what's called a decrementing function. So what does that mean? This is a function that maps the values of the formal parameters to a non-negative integer. Right? In some sense, this is giving us the size of the problem. And if I can find a decrementing function, something that says, given the values of the parameters, I will take those values and map it into an integer. That decrementing function has to have 2 other properties. The first is, when the value of that function is less than or equal to 0, the recursion is going to terminate. And the second one is, for each recursive call, the value of that function is strictly less than the value on entry to the instance of the function. In other words, the decrementing function will have some value when I start the recursive call, and when I return from the recursive call is smaller. Said very simply, this decrementing function should capture the size of the problem, and I want it to be the case that that function is smaller on the recursive call and smaller on the next recursive call, and when it gets down to or below 0, the recursion terminates. Again, a lot of words. For this particular case, the function is very simple. It's just high minus low, right there. High minus low is telling us the range of the list still to be searched. And let's check it out. It's at least 0 the first time it's called. Okay, that's good. So it's going to be something that's a non-negative integer. When it gets down to being exactly 0, when high is equal to low, oh, that said, I have no recursive call and I just return a value. Okay, so that's done. And otherwise, what's happening? Well, it's going to either halt or recursively call with the value halved each time. Because at each case, either high is decreased by half or low is increased by half. And so it's going to reduce the value at each time. So by finding that decrementing function, I've just proved that my recursive procedure actually terminates. Great. So I got something that does the search properly. Again, another way of thinking about this is just the range left. That's why I'm reducing it each time. So I got something that actually works. What's the complexity? Well, how many recursive calls are there? Why do I ask that? Well, we know that the work within each call is constant. We're just doing an access to a list and comparing it, and we're doing some computations of some simple arithmetic values. So how many recursive calls do I have? Well, that can be answered by saying, how many times can I divide high minus low in half before it reaches 0? And why is that important? High minus low is the range of the problem left. On each recursive call, I'm splitting it in half, and I'm splitting it in half, and I'm splitting it in half. How many times can I keep splitting something in half until I get down to something that's basically of size 1? And that we already have seen before. That's log base 2. Basically, at each step, I'm dividing by 2. So after log base 2 calls, I'm done. So the complexity here is ordered just log of the length of the list. And that's nice. We know that's a very efficient algorithm. So this is much better than linear. It's going as the log of linear.